MCV4U1 Chapter 4 Curve Sketching Session 11. In this session, we work on an algorithm, a complete algorithm for sketching the graph of a function. The step 1 in the algorithm is finding any limitation in the domain of the function and determining any discontinuities. Step 2, finding any vertical asymptote. Step 3, determine any intercepts. Step 4, determine any critical number by finding the derivative and setting the derivative to 0 or undefined. Step 5, determine the interval of increase-decrease by drawing the sign chart for the derivative, and then test critical points that we found in step 4 to see whether they are local maximum, local minimum, or neither. Step 6, determine the behavior of the function for large positive and large negative values of x. If x can approach to positive or negative infinity, we find the limit of f of x. This will identify the horizontal asymptotes, if they exist, identify the function's value, the function's values approach to the horizontal asymptotes from above or below. Determining the second derivative and test for points of inflection using the interval of concavity. Step 8, determine any oblique asymptote. Identify if the function values approach the oblique asymptotes from above or below. And step 9, putting all of this together and sketch the graph of the function. When we use this algorithm, we have to keep in mind that we will not use all steps in every situation. Use only steps that are essential. We are familiar with the basic shape of many functions that can help us to sketch the graph. What we learned in this chapter, if the derivative of a function on an interval is positive, function is increasing on that interval. If the derivative of a function is negative, function is decreasing on that interval. If the sign of derivative is changing from positive to negative, we have a local maximum. If the sign of derivative is changing from negative to positive, we deal with a local minimum. Second derivative on an interval positive means function is concave up on that interval, and second derivative negative means function is concave down. Point of inflection is the point at which the sign of second derivative is changing. Let's start with an example. Use the algorithm for curve sketching to sketch the graph of f of x equals negative x3 minus 2x2 plus 5x. This function is a polynomial. The domain of function is all real numbers. It's always continuous, and we do not have any vertical asymptote. If we set y to 0, we deal with a cubic equation. We solve the equation by factoring. X is common factor, and then 3x2 plus 2x minus 5 can be broken down to 3x plus 5 times x minus 1. Therefore, 0, 0, minus 5 over 3 and 0 and 1 and 0 are the x-intercepts. Critical numbers, we find the derivative, set it to 0, and by factoring, we find x equals 5 over 9 or negative 1. Second derivative is negative 18x minus 4. At 5/9 second derivative is negative, at -1 it is positive. Therefore 5/9 is locating a local maximum and -1 local minimum. Second derivative test. If we draw the chart for the interval chart for second derivative, less than -2/9 function is concave up, more than that number, more than -2/9, it is concave down. -2/9 is the x coordinate of the point of inflection. By second derivative test, we found that x equals 5/9 gives a local minimum and x equals -1 gives a local maximum. If we draw the sign chart for the first derivative, we can find the interval on which the function is increasing or decreasing. We have a minimum, a maximum. We know point of inflection is at x equals -2.9. Limit of y as x approaches -infinity is positive infinity. Lim of y as x approaches positive infinity is negative infinity. The dominant term in the function is -x3. By joining these points, we have the graph of the function. Next example. It's a rational function. F of x equals x minus 4 over x2 minus 2x minus 2. The x-intercept is 4 and 0. When numerator is 0, we find x equals 4. When x is 0, y is 2. Y-intercept is 0 and 2. We set the denominator to 0 and we find x equals 2 and x equals -1 as points of discontinuity. Domain of the function is all real numbers except x equals 2 and -1. These are vertical asymptotes since the numerator is not 0 at these 2 points. We find limit of f of x when x is a little bit more than 2 and a little bit less than from right side and left side of 2. When x approaches 2 from the left side, the numerator is negative, the denominator is negative, therefore the function is positive and the limit is positive infinity. This way we know the graph of the function near asymptotes. Let's find limit of f of x as x approaches -1 from the right side. The denominator is x minus 2 times x plus 1 and the numerator is x minus 4. When x is around -1, the numerator is definitely negative. X minus 2 is also negative. Since x is less than -1, x plus 1 is also negative. This means when x is near -1 and is smaller than -1, the fraction is negative. Numerator is a number, denominator approaches 0. As x approaches -1, numerator approaches -5, and denominator approaches 0. Therefore, the limit is -infinity. This means the graph of the function is getting close to the vertical asymptote from left side this way. The next part is finding the derivative, setting derivative to 0. We're doing this, x would be 4 plus minus square root of 10. Finding the critical numbers. We draw the sign chart for derivative. For less than -1, derivative is negative. For x is between -1 and 0.8, it is negative. Between 0.8 and 2, positive. Derivative is positive when x is between 2 and 7.2, and it is negative when x is more than 7.2. 7.2 and 0.8 are the critical numbers. This way we know when the function is increasing and when it is decreasing. As x approaches infinity, y approaches 0. This can be done by factoring x2 at the denominator and finding the limit. Or there is a rule that says when the degree of denominator is more than the degree of numerator, limit of the fraction as x approaches infinity is 0. By checking a number, a positive and big number, we can see when x approaches infinity, it's going to be from above. Now we put all this information together and we sketch the graph. We have a minimum point, we have a maximum point. The minimum is at x equals 0.8, and the maximum is at x equals 7.2. Put this information together and sketch the graph of the function. So in this section, we basically put everything together to sketch the graph of a function. Finding the domain, finding the intercepts, finding the asymptotes, finding the critical numbers, finding the interval of increase-decrease, finding when the function is concave up and when it is concave down, end behavior when x is close to the asymptote or when x approaches infinity. Put all of this together and sketch the graph of the function. To understand this algorithm better, next session we work on questions on page 212 and 213. We solve question number 6, 7, and 10. Thanks for watching.